Swayam Prabha. Digital India. Educated India.
Hello all, welcome to the lecture 6 of this course. Till today we have discussed about basics of aircraft wings, aerofoils, their geometries, lift curve slopes, different types of drags, alright, but we haven't still studied the environment in which the aircraft will fly, alright. So the pressure, the properties like pressure, temperature, density, they not only depend upon the altitude, but also the latitude, the longitude, what is the season, what is the time. So taking all these things into considerations while designing aircraft is actually impractical. Hence, the standard atmosphere is defined. So standard atmosphere gives the mean values of pressure, temperature and density as a function of altitude. Alright. So there are different atmospheric layers that I'm sure you must have studied in your high school physics. Let us revise those first before we get into standard atmosphere. Alright. Now let us revise our basics on layers of atmosphere. So there are different layers: troposphere, stratosphere, mesosphere, thermosphere and exosphere. Alright. So in troposphere, so this part of atmosphere is the densest, where the temperature is around minus 15 degrees Celsius to minus 56 degrees Celsius. So air pressure at top of the troposphere is only 10% of that at the sea level. Alright. So that means 0.1 atm. So almost all general aviation or turbojet and jets fly in this layer. Alright. So that is 0 to 11 kilometers. Next is the stratosphere. So here the airflow is mostly, horizontal. So the temperature is around minus 56 degrees Celsius to minus 3 degrees Celsius. So the ozone layer that we basically talk about, which absorbs harmful ultraviolet radiation, is actually present in this layer. Alright. So 99% of the air is located in troposphere, that is approximately 80%, and stratosphere approximately 19%, 19. Alright. So modern jet aircraft, they cruise in this lower stratosphere. Even the supersonic passenger aircraft Concorde, which actually retired in 2003, that also used to fly in stratosphere. Okay. So next is the mesosphere. So at the altitude of 65 kilometers, the aerodynamic heating of the space shuttle during re-entry into Earth's atmosphere from the space, so that becomes important phenomenon. So no modern aircraft is able to fly in this layer due to the lack of sufficient air in mesosphere, which is about from 50 to 80 kilometers, and the temperatures will be around even minus 93 degrees Celsius. Alright. Next is the thermosphere, which extends up to 800 kilometers, and here also we have a Karman line, start of the outer space. So what happens in this layer? So chemical reactions occur much faster here than on the Earth's surface. Here density is so low that one gas molecule can travel 1 kilometer without colliding with another molecule. Alright. So a regular thermometer also will not be able to measure the 1500 degrees Celsius over here. Thus the concept of temperature. Now what is temperature? Kinetic energy with which the molecules move, right? So the concept of temperature loses its traditional meaning and may not be associated with the terms hot and cold. Okay. So also ionosphere lies within thermosphere. Finally we have exosphere, 800 kilometers and above, where we have spaceships. So this is the outermost layer of Earth's atmosphere. Alright, so the temperature can vary from absolute 0 to 2000 degrees Celsius. So the particles present here escape into the space. Alright, so this was brief about the layers of atmosphere. Now let us quickly begin the standard atmosphere. So before that we need to define the altitude, definition of the altitude. Alright. Okay, assume this is the aircraft. Okay, and this is the curved surface of the earth. All right. So this is the radius. Radius of earth, and this is the altitude till the surface of the earth, hg, we call it as absolute geometric altitude, and this is the ha, which is till the center of the earth. Okay, so let me write here r is radius of earth, ha is absolute altitude, okay, that is distance of the aircraft till the center of the earth. Okay, next is hg, geometric altitude, okay, this is the distance till the surface of the earth. All right, so now we can write ha equals hg plus r. Okay, all right, now let us quickly find out the relation between, you must have studied about Newton's law of gravitation. All right, because here we are interested in finding out the variation of gravity. Okay, variation of gravity with altitude. Fine. How local g varies with ha, that is absolute altitude. All right, okay, now from Newton's law of gravitation, consider two bodies, that is between two bodies. I'm sure you must have seen this equation, Newton's law of gravitation, F equals to capital G, small m, and capital M, that is between the two bodies, and divided by r square. All right, G is the gravitational constant. So flight vehicle in the air, so for example, if flight vehicle in the air, we can write F equals to G M M, total altitude is hg plus r whole square. All right, now what is F? Mass into acceleration, m into g, m upon hg plus r whole square. So this will get to g equals to capital G is capital M by hg plus r whole square. So let me take this as equation number 1. All right, now consider when the flight vehicle is in contact with the ground. Okay, when flight vehicle is in contact with ground, so that means your hg will be equals to 0, and your acceleration of the gravity will be equal to local acceleration of gravity at the sea level. Okay, so when I'm writing this subscript g naught or naught, that generally means sea level conditions. All right, sea level. All right, so now we can write force equals to F equals to G M M. So here it will be capital R square. All right, only R. Okay, now substituting F equals to mg naught, since we are talking about sea level conditions. Alright, so now I can write G naught equals to capital G capital M by R square. Let me take this as equation number 2. So now I'll divide 1 by 2. Okay, so we get G upon G naught equals to GMM. No, it will be R capital R square by R plus HG whole square. Alright. Okay. Now this is the relation between the local acceleration of gravity and the acceleration of gravity at the sea level. Okay, let me take this as equation number 3. So this equation will be useful in determining how pressure, temperature and density actually varies with the altitude. Okay. Now we need to know how the pressure, temperature is actually varying with the altitude. So there is an equation which will help us in deriving those relations. That is hydrostatic equation. Alright, so let me write here. So this equation allows us to calculate pressure, density, variations as a function of altitude. As a function of altitude. Alright, so let me draw a figure over here. Let me draw a cuboid. Alright, so here we are interested, consider any fluid element. For example, consider any this fluid element. Alright, consider any fluid element over here, which is infinitesimally small fluid element at rest. Okay, now consider the dimensions of these cuboid as unity. This one also as unity. And since we are interested how the properties are varying as a function of altitude, we'll assume this one as a small altitude, that is DHG. Okay, small altitude DHG. Now there will be some pressure at the bottom surface of this cuboid and there will be some pressure top surface of this cuboid. So let us assume there is the pressure at the bottom surface is equals to P, and since this properties is a function of altitude, so there will be a change in pressure at the top surface. Now this is the top surface. So here pressure will not be P, it will be something different than P. So let me assume here P plus some change in pressure dP. Alright, so here in this direction we have increasing altitude Hg. Okay, so here we assume that this hydrostatic equation, which will be illustrating force balance on an element of the fluid at rest. Okay, so we are assuming the fluid element is at rest. Okay, so where bottom and the top surfaces or faces have sides of unit length and infinitesimally small height, that is dH. Okay, so then what will be the pressure at the bottom face? Okay, on bottom face the pressure P is felt, of course, Alright. So pressure is given by force upon area. Right. So let me denote this as FB, that is at the bottom. FB equals to pressure into area. Okay. Now what is area over here? That is 1 by 1 cross 1. This is 1 and this is 1. Alright. So here FB, force on the bottom face, will be exactly equals to P. Okay. So top surface again is a slightly higher altitude by how much? By dHg. And because the pressure varies with altitude, the pressure on the top face will be different by infinitesimally small value, that is P plus dP. Okay. So similarly, we will be finding what is the pressure acting on this top face. Alright. So let me write here Ft equals to, again, pressure into area. Now what is pressure over here? Pressure is P plus dP. Area is 1 cross 1. Ft equals to P plus dP. Alright. So we have force on the bottom and the force on the top surface. So we have now force at the bottom as well as on the top. So now we can easily find what is the volume of the fluid element. So volume is 1 into 1, of course, into dHg, length into breadth into height. So that is again dHg. Now what is the mass of the fluid element? This fluid element. Alright. So mass of the fluid element is what? Density into volume. Right. Remember, density was mass upon volume. Alright. So mass is density into volume. So let me consider density as rho into volume. Volume we have already calculated, dHg. So this becomes rho dHg. And similarly, after mass, we can easily find what is the weight of this fluid element. Alright, weight is given as mass into gravity. So here we have rho g dHg. Alright, so now focus here. This fluid element is actually not moving. Okay, this is actually in balance. So since the fluid element is not moving, the forces which are acting on this fluid element must be balanced. The forces which are acting on this fluid element must be balancing out. Alright. Now what are the forces which are acting on this fluid element? Okay. So one is this pressure at the upward direction, this P plus dP at the downward direction at the top face, and the third will be obviously the weight of the fluid element. Okay. Now weight will obviously be acting at downward direction, and this P plus dP is also in downward direction, and in the upward direction we only have P. Okay, so we have to equate those forces. So since the fluid element is not moving, it is not moving. So three forces that we have just talked right now, the three forces, that is pressure, on top, bottom, and weight must balance. Okay, so now I can write P equals to P plus dP plus rho g dHg. So what do we get? dP equals to minus rho g dHg. Okay, so this equation is known as the hydrostatic equation. This is the hydrostatic equation. Okay, so this applies to any fluid, not only air, it applies to any fluid. So now if you notice here, so this looks like a sort of a differential equation. Alright, it is a differential equation where dP and dHg are the differentials. So we can actually integrate this equation, to get the pressure. Alright, but the problem here is, here G is not constant. G is not constant. So it becomes difficult to integrate this equation since it is a variable and it is depending upon the geometric altitude. Alright, but to make things simpler, we'll assume G is equals to G naught. We'll come to the reason as well why we are taking this assumption. As of now, assume G equals to G naught, that is at sea level. Okay, so now this equation will become dP equals to minus rho G naught, we write here dH. Alright, so let me take this as equation number 3. So one thing you must have noticed here, I have mentioned of course G as G naught, but instead of dHg, I mentioned here dH. Alright, the reason is, yes, because this is an equation, so LHS must be equals to RHS. Since we are changing this G to G naught, so there must be a change in H. There must be a change in the altitude. So this altitude we call it as geopotential altitude. Okay, just remember that this is a fictitious altitude. Okay, this is not real, this is fictitious, only used for calculations. Alright, we only did this because we wanted to make these two equations as identical. Okay, so that's why we used dH instead of dHg to compensate our assumption. Alright, so this is done to compensate our assumption. Now there must be a relation between this dH and dHg, right? So now we'll find that relation. So now we'll divide this equation dividing 3 by 2. So let us assume this is equation number 2. So we'll get dP upon dP minus rho G naught dH by minus rho G dH G. So G naught by G, dH by dHg. Okay. So now, does this sound similar? G naught by G. Remember, we have already found the expression for G by G naught. Okay. So that is why we have derived this relation between G and G naught, which we will be using here. So using that equation, G by G naught was R square by R plus Hg whole square. So if we use this relation, what do we get? So this dP by dP becomes 1. So 1 equals to R plus Hg whole square by R square. So dH by dHg. Alright. This becomes dH equals to R square by R plus Hg whole square into dHg. Okay, so now we are able to integrate this equation and find the relation between the geometric altitude as well as the geopotential altitude, which is nothing but a fictitious altitude. Alright, so let me write here integrating from 0 to h and 0 to hg. Okay, so we are integrating from sea level since conditions are known at sea level. Alright. So let me do the integration for you. So 0 to h, we have dh. 0 to hg, we have r square pi r plus hg whole square dhg. So this is into dhg. So this easily can be written as r square. Since radius of earth is constant, it comes out of the integration 0 to hg, where we have 1 by 1 plus r plus hg whole square into dhg. Okay. Now I am expecting you to do integration over here. Okay, this is not that difficult, but let me do it for you. So this becomes h easily. Then we have r square. Alright. So this, the integration variable is hg over here. So this is 1 by x, that is x power minus 1. So the integration will become, yes, you just have to use that equation, minus 2. This is, in the denominator we have minus 2. So this becomes minus 2 plus 1, and r plus hg will be to the power minus 2 plus 1. So this will be 0 into hg. Okay. So finally we can write here r square into minus 1 upon r plus hg, 0 to hg. Alright, and then substituting this hg over here. Okay, so r square minus 1 upon r plus hg minus from minus 1 upon r. Okay, so here hg will become 0 over here. So now h equals to r square. The denominator we have r into r plus hg. Okay, so this becomes minus r plus hg. Okay, just taking the LCM, and we have r square hg upon r into r plus hg. R into r plus hg. Now this further can be reduced to h equals to, let me write here the final expression, h equals to r pi r plus hg into hg. Alright, so this was the relation that we were looking after since we have defined a new variable, geopotential altitude. So let me consider this as equation number 4. Alright, so this is the relation between h and hg. Now consider for very low altitudes, when hg is less than or equals to r. So then what happens? So we can ignore this hg over here. So then what happens? The geopotential altitude will be r by r plus 0 into hg, and h will be exactly equals to hg. Alright, so now let me give you an example. So if we consider altitude, geometric altitude hg equals to 10 kilometers. Okay, this is where our most of the aircraft fly, right? That is why I have considered this assumption. They consider geometric altitude as 10 kilometers and equatorial radius of the earth. Okay, equatorial radius of the earth, assuming it to be approximately 6400 kilometers. Alright, now that we know these two terms, so then we can find the geopotential altitude, h equals to, so 6400 pi 6400 plus 10. So noticing this is 6400 and we are adding only 10 kilometers. Okay, So now this will become 9.9843 kilometers. So noticing the change, geometric altitude was 10 kilometers and geopotential altitude has only been reduced by this much value. It is approximately 10 kilometers only, okay, but slightly less than 10 kilometers, of course. It is 9.9843 kilometers. So can you find the percentage of error over here between the geometric and the geopotential altitude? Okay, so as engineers, we are interested to know what is the percentage of error. All right. So let me write here 9.9843 minus 10 by 10. Of course, you have to take the absolute value of this to find the percentage of error. So the percentage of error is 0.157. All right. So it is not even 1%. So not even 1% of error. All right. So this is mostly or equals to the geometric altitude. All right. The percentage of error is not even 1%. Now, when does this start giving a significant error? Okay, so this question must comes to your mind. If not 10 kilometers, then at what kilometers this error becomes significant? So let us see at 65 kilometers. Okay. So this is where actually our aerodynamic heating of the re-entry vehicles happens. Okay. Aerodynamic heating of re-entry vehicles. Okay, so here the error exceeds 1%. Okay, so check this by yourself. All right, I am giving this an exercise to you. Check this by yourself. Will the error indeed be greater than 1% or not? Okay, so now we are in a position to obtain pressure and density as a function of altitude. Okay, pressure density as a function of altitude. Now, why I have not written temperature over here? What happened to temperature? What do you think? Why have I not mentioned temperature over here? So, let me show you an image. Now, we have balloons and rockets, right, which are actually able to measure the temperature at 10 kilometers, right? So thanks to these weather balloons, which is up to 30 to 40 kilometers, the balloons can even measure up to 30 to 40 kilometers altitude. And there are sounding rockets. And these are the sounding rockets. They can go from 40 to 120 kilometers altitude. All right. So with this, we have been able to measure the temperature at these altitudes. All right. So these have been existing for quite a while now. So with the help of these, we have the temperature profile as a function of altitude. Okay. So let me draw the variation of the temperature as a function of altitude. All right. So here in this axis we have altitude. Okay, let me write in kilometers. And in this axis we have temperature. Okay, Kelvin. All right. Let me here write here. This is 0. So this is 200, 240, and this is 280, 320. This is in Kelvin. So this range is 11 kilometers. This is 25 kilometers, 47 kilometers, 53 kilometers, 79, 90. Alright. So here this is still 20 kilometers. This is here 40. This is here 80. This is 60. And this is 100, approximately 100 kilometers. Alright, so let me write the values over here. So this represents 0 kilometer, that is the sea level conditions. So here the temperature is 288.16 Kelvin. And if you notice here, this is almost like a linear curve. So here the slope I am representing here as A1, slope of this linear curve, that is how the temperature is varying with the altitude. So this is minus 6.5 into 10 to the power minus 3 Kelvin per meters, right? Kelvin per meters. So if, what about 11 to 25? So here we have temperature almost constant here. Okay, so temperature is around 216.66 Kelvin. Now again, after 25 kilometers, temperature has started increasing with this slope. So this slope I am mentioning here as A2 is 3 into 10 to the power minus 3 Kelvin per meters. Okay, and again the temperature is constant from 47 to 53 kilometers. So here temperature is approximately 282.66 Kelvin. Again temperature started reducing in this layer. So we have slope given here at A3 equals to minus 4.5 to 10 to the power minus 3 Kelvin per meters. Here the temperature is 165.66 Kelvin from 79 to 90 kilometers. And this is another slope, that is A4, 4 into 10 to the power minus 3 Kelvin per meters. Okay. Alright. So this is the temperature profile of how it is varying with the altitude. Okay. So now what we'll do here is, now see the vertical lines over here. So these vertical lines are constant temperature. Okay. So these are, we call it as constant temperature as isothermal layer. And we have this inclined or the linear curves. So these inclined lines represent gradient regions. Okay. These inclined lines are gradient regions. Alright, so we are more or less are interested till, this layer till 25 kilometers, where we can actually find the relation between pressure, temperature and density. In fact, this is the function of temperature with the altitude. So we'll be finding the relation for these two layers only, that is isothermal layer, where the temperature is constant from 11 to 25 kilometers, and the gradient layer from 0 to 11 kilometers. Alright, that is what we want. Now remember, we had this equation dP equals to minus rho g naught dH, है ना? Yeah, dP equals to minus rho g naught dH, equation number 3. Alright, where we introduced actually the fictitious altitude. Okay, so now we divide this equation So this was equation 3. What we'll do is we'll divide equation 3 by equation of state. Remember what was equation of state? I'm sure you must have studied. That is perfect gas equation. है ना? P equals to rho R T. Okay. This is the perfect gas equation. R is the universal gas constant, where R is the universal gas constant. Which is approximately 287 joules per kg Kelvin. Okay. So when you divide this by this equation, so then we get dP by P equals to minus G naught by RT into dH. Okay. So let me take this as equation number 5. Alright. Now for sea level conditions, we already know what is the value of pressure, temperature and density. So you should always remember the values of pressure, temperature and density at sea level. So at sea level we have P naught equals to 1.01325 into 10 to the power of 5 newtons per meter square. Alright. So this can also be written as 1.01325 10 to the power 5 pascals. Okay. So we know 1 pascal is 1 newton per meter square. And in terms of bar, you can write 1.01325 bar. Okay. Similarly, density at sea level is of course 1.225 kilogram per meter cube. And the temperature at sea level, I have already mentioned here, it was 288.16 Kelvin. Okay. So always remember at least sea level conditions, 288.16 Kelvin. Alright. Now first we will be considering the gradient layer. Alright. So say for example we want to find the properties at 5 kilometers. Okay. We want to find pressure, temperature and altitude. Pressure, temperature and density at 5 kilometers altitude. Okay, so that is in between 10 and 11 kilometers. We already know what is P naught, rho naught and T naught at 0 kilometers. Now we are interested in finding pressure, temperature, density at 5 kilometers. Okay, so that is the intent right now. Okay, so now we'll proceed further. How we can find the pressure, temperature and density at 5 kilometers. So what we'll do is we'll see that the temperature variation again is linear from 0 to 11 kilometers. Alright. So this variation can be written as, that is the slope is written as dt upon dh. What was dt upon dh? This A1. Okay. So this is the slope. So dt upon dh equals to temperature at 5 minus temperature at 0 kilometers. So this is altitude at 5 minus altitude at 0. Okay. So remember this altitude we are talking about is geopotential, not geometric. Okay. So this, let me consider this as A. So here A is actually a lapse rate. Or in other words, of course, we can call it as slope. Okay, so A is the lapse rate. So A equals to dt upon dh. Alright. So dh we can easily write dt upon A. Wonderful. So now we are in a position to integrate from 0 to 5 kilometers. Integrating from 0 to 5 kilometers. So we'll write here 0 not 0. Let me write here P naught, the pressure at 0 kilometers, pressure at 5 kilometers. So dp upon P equals to this equation. Okay, so I'm talking about this equation, equals to minus G naught by AR integration T naught to T5. So here we have dt upon T. So these were constants, right? So G naught is a constant, lapse rate is a constant, R is universal gas constant, that is also a constant. So now you understand why did we take assumption that G naught is a constant. So this has made things simpler for us. So now G naught has come outside because it is a constant, and now it is easy to do integration of this, that is dt upon T. Alright. So now what is the integration of 1 upon x? Yes, so that is ln of P5 upon P naught. Alright, minus G naught upon AR ln of T5 upon T naught. Okay, so now we can write P5 upon P naught as P5 upon P naught as T5 upon T naught. So this will go to the power minus G naught power AR. So taking exponential of in the both sides, alright. And this will go to the power of T5 upon T naught. Alright. So now this is the equation. Now look at this equation carefully. We know T naught, we know A, lapse rate, we know universal gas constant R, we know G naught, we know P naught. What about T5? Okay, so even though we have the table here, the plot here, we can still find the variation of temperature T5, okay, because it is a linear curve. Alright, so T5 equals to T naught plus dt upon dh h5 upon minus h naught. Okay, so do not forget linear equation, straight line equation, y equals to mx plus c. Alright, so this equation has come from this. This is the T naught, that is the intercept, this is the slope, and this is the x variable, that is h5 minus h naught. Okay, so let me write here T5 equals to T naught plus, this is the slope dt upon dh, and let me write here delta h. Alright, so now we know T5 also. This T naught is known, slope is known, and of course we know the altitude at which we want to find the properties. So h5 minus h naught, that is delta h. So now T5 is a known quantity. Alright, so what we do is, now we have T5 also, now we have P naught also. Okay, so now we can easily find what is the pressure at 5 kilometers. Alright, now let us find density. Okay, so now let me again write equation of state at 0 and 5 kilometers. Remember, equation of state at 0 and 5 kilometers is P naught equals to rho naught R T naught, and similarly at 5 kilometers P5 equals to rho 5 R T5. So universal gas constant will remain same. Alright, only the other parameters will vary, and if you divide this equation, so we get P naught upon P5 rho naught upon rho 5 and T naught upon T5. Now what we were interested in finding, density at 5 kilometers. Alright, so we write here rho naught upon rho 5. We will take other terms to the other side. So we have, let me write here this rho 5, since we are interested in finding rho 5 directly. So rho 5 upon rho naught, P5 upon P naught, and it's T naught upon T naught upon T5. Alright. Now we can easily find what is the density at 5 kilometers. So rho naught, so rho 5 upon rho naught equals to T5 upon T naught power minus G naught by AR. Alright. And let me also inverse this, T5 upon T naught power minus 1. So I've just substituted P naught upon P5 in this equation. Okay. Fine. Now finally I can write rho 5 upon rho naught equals to T5 upon T naught. Let me write here minus, let me take it common, G naught by AR plus 1. Okay, this is this power. And finally we can easily find what is the density at 5 kilometers. So since rho naught is also known, T5 we also found. Okay, you can easily find this relation. Still, remember this is still what kilometers? This is still 11 kilometers. Okay, so this layer, gradient layer, this is applicable till 11 kilometers. Okay, now next we'll focus on considering isothermal layer. Okay, the isothermal layer, here we have temperature as constant. So that means temperature will remain at 216.66 Kelvin. So temperature at 25 kilometers, at 11 kilometers, that will remain same. So now temperature is a known quantity in the isothermal layer. Alright. Now let us say that you want to find the pressure and density at 20 kilometers, 20. Okay. So how do you do that? Now we know the pressure, temperature, density at 11 kilometers. Now the question is, how will you find the pressure and density at 20 kilometers? Alright, in the isothermal layer. Okay. Now we'll follow the similar procedure. We'll integrate our equation number 5 again that we have used before from 11 to 20 kilometers. Okay. What was the equation? dP upon P equals to minus G naught by RT dH, right? Equation number 5. Remember? Now we have to just integrate those equations from P11 to P20. So dP upon P minus G naught by RT integration, this is dH. So this is H from H11 to H20. Alright. Now again you can see here the significance of the assumption that we have taken before. Here G naught is again a constant. It has come out. So it has made our life easier. Right. So we can easily integrate this equation now. Now again integrating this equation. So we get ln of P20 upon P1 minus G naught upon RT. So H20 minus H11. Alright. So now this can be easily written as P20 upon P11. I'm taking exponents again. So e power minus G naught by RT. Okay. So H20 minus H11. Alright. So this is the expression for P20. P11 is known quantity and these are also known. Okay. So now again using equation of state at 11 kilometers and 20 kilometers. Okay. Using equation of state. So at 11 kilometers we can mention P11 equals to rho 11 R T11, and at 20 kilometers P20 equals to rho 20 R and T20. Okay, so here R is universal constant, that will remain constant, and again we divide this equation. Okay, so we can write rho 20, since we are interested in finding now density at 20 kilometers. So rho 20 upon rho 11. Okay, this will be same as P20 upon P11. All right, so this will become, why it is same? Because here temperature at 11 and temperature at 20, it is same. Okay, so that gets cancelled. R also goes. So this is the same expression, that is e power minus G naught by RT. Okay, so H20 minus H11. So you get the same expression over here. So here we know the value of density at 11 kilometers. So now these values of pressure, temperature and density are tabulated. Okay, so even you must have seen few tables, atmospheric tables. So in atmospheric tables, you will be basically seeing the variation of pressure, temperature and density as a function of geopotential altitude h and also as a function of geometric altitude. So I encourage you to look at these tables, that how the pressure, temperature and density, they are varying as different altitudes. Alright. So this is how you find pressure, temperature and density at various altitudes. So I recommend you to look at those tables where we can easily see the variation of pressure, temperature and density as a function of both the geopotential altitude as well as geometric altitude. So in the next lecture, we'll be doing a MATLAB simulation of this pressure, temperature and density altitude at various, using the MATLAB simulation. Alright. Thank you.